All right, guys. Well, I think I'm going to go ahead and get started. We've got quite a few people here. I am also recording this session that we are starting right now. So if you miss something or you have to leave early or anything like that, you can always watch this video again later. I made a new tab on my Math 407 website for class lectures. And I already posted the one from Tuesday. And then, of course, later today, I'm going to post this one as well so that you guys can always go back and watch this stuff later if you miss anything. Actually, I was told that I'm not supposed to actually do like a formal lecture today. Let's see, just a second. I've got a few more people trying to come in the room, and I've also got Tim. You're having trouble with the audio, I see. Unmute or join with computer audio. You should be able to get some sound. What you could do, Tim, if you wanted to try again, is you could leave the Zoom room and come back in one more time. And when it asks you to join, you should be asked to join with computer audio. I'm hoping that's the way it's going to go. Is anybody else having trouble hearing me? Is most of you okay? Edith, can you hear me? Yeah, okay. So a lot of you can hear me. I think Tim's going to try this again, restart. Anyway, what I was saying is that I'm technically not even supposed to do a lecture today. The university kind of has these like down days right now to kind of give everybody time to adjust to the new virtual learning environment that we're using. So I'm going to be very careful what I talk about today. I'm going to answer some homework questions, and then I have two group works. One of them is a leftover group theory group work, and then there's another one that I just posted earlier today that is from the beginning of the ring theory material. And so my idea was just to go over some homework questions and then try those group works, keeping in mind that if you miss anything, the solutions to those group works are posted, and you'll be able to obviously get those things in real time. As I told you on Tuesday, if you're using headphones, you certainly can unmute yourself. If you're not using headphones, you also can unmute yourself if it's quiet in the background, and as long as, you know, I mean, especially if you have something you want to ask me, just be sure to unmute yourself, and then you can certainly ask away. So I'm going to start by opening it up to you guys to see, would anybody like me to go over any of the homework problems that are due today? Like, I'm happy to just work some of them out. You can either type the question number you're interested in the group chat, or you can unmute yourself and just tell me verbally where you might be stuck, and I'm happy to help.
Hi, Dr. Annan.
Hi, Edith. Do you have a question?
Yes, on section 9.3, number 22, it's the one where we have to use the peacock argument.
Okay, so let me write it down. This is number 22 in 9.3, and we have two primes, P and Q. I'm just going to kind of write this on the board for people. And we're looking at a group G, and I'm going to assume that the size of the group is P squared times Q. Okay, and P and Q are two distinct primes, right? Yes. Okay, so what I would suggest on this problem, for those of you who are still working this out, is that we look at the Ceelo, the third Ceelo theorem, because it's going to tell us something about the number of Ceelo subgroups that we have. So for example, we can count the number of Ceelo P subgroups, which has to be one more than a multiple of P, and has to divide the rest of the factorization of the group size. In this case, that would just be Q. Okay, so it would be something like this. All right, and so the number of Ceelo P subgroups has to divide this prime number Q, right? So we have n sub P dividing Q. But of course, the only divisors of a prime are 1 and itself. So what we already know is that n sub P is equal to 1 or n sub P is equal to Q. Okay, so those are the two choices, right? Let me just make sure I'm not blocking the screen here. Now, the first case, if there's only one Ceelo P subgroup, then we would be done because that Ceelo P subgroup would be normal in the group, right? So we would have a normal subgroup, and we could just simply use the definition of simple and say that there's no, that G is not simple. So let's assume that the number of Ceelo P subgroups is Q for a second, okay? And let's take a look at the other the other prime, which is Q. So the number of Ceelo Q subgroups would be something of the form, 1 plus a multiple of Q, and that would have to divide P squared, okay? So now P squared has 3 different divisors, right? There's 3 different numbers that we could have here. We could have n sub Q equal to 1, or could be equal to P, or could be equal to P squared. Can everybody see that all right? So let me just pull this a little bit closer here. So there's 3 possibilities here. So we have n sub Q is equal to 1. Of course, this case, we're also done, again, by the same reasoning as before. Or we have n sub Q equal to P, or n sub Q equal to P squared, right? These are the choices that we would have. Okay, so where do we go from here to figure out sort of what the possibilities are? They didn't tell us, which of these primes was bigger. These are just 2 distinct primes, so it's not totally clear which case that it would be. But I mean, if n sub P is equal to Q, let's go back over to here again. If n sub P is equal to Q, then what that means is that 1 plus pk is already equal to Q. And that tells me that Q is actually larger than P.
Dr. Adden, can you move it over a bit? We can't really see what you just wrote.
See what I just wrote. Let me back this up a little bit. Is that better?
Yeah, there's a little bit of glare, but oh yeah, that's good.
Because I've got a lamp on. If I turn that lamp off, it gets really dark. So is that a little bit clearer now?
Yeah, yes, that's better. Thank you.
Okay, so all I was saying is that because we are assuming that n sub P is equal to Q, I know that 1 plus pk is equal to Q. That actually tells me that Q is bigger than P, right? Q would have to be bigger than P in that situation. So if Q is bigger than P, then 1 plus QL could not be equal to P, because Q is bigger than P. So how could 1 plus a multiple of Q be equal to P? If Q is bigger than P, that can't happen. So we now can rule out that case, right? So this is impossible. I'll just squeeze this in over here. Impossible since Q is bigger than P. So what we're left with are these 2 boxes over here on the far right of the screen, which I'm hoping is still in view. Yeah, it is. Okay. So let's start thinking about, I'm going to go ahead and erase some of this stuff that we have so far. Again, this is all being recorded, so you'll be able to go back to it. If anybody else is having any questions, just feel free to speak up.
The NP equals Q, that's an assumption we're making, right? That's like a case we're going to explore?
Yeah,
Or
because
do we
the
yeah.
only other choice is that n sub p could equal 1, but in that case, we're already done. So we may as well assume that n sub p does not equal 1, and that means it has to equal q. So at this point, I'm assuming that. And based on that, I can also therefore claim that n sub q is equal to p squared. This is the only case that we're not really done yet. Okay, you with me? Okay, so right, so we have this situation here. Now, that means that we have q Ceelo p subgroups, and we have p squared Ceelo q subgroups, right? Which of those numbers do you want me to, or do you think we should play with first? Like, I'm just wondering whether the n sub p or the n sub q might be. Which one is easier to work with, the Ceelo p subgroups or the Ceelo q subgroups?
The Ceelo Q subgroups?
Yeah, you're right, Sergio. It's the Ceelo q subgroups. The reason is that the size of a Ceelo q subgroup is just q, which is a prime. The problem with working with the Ceelo p subgroups is that they have size p squared. They have size p squared. A Ceelo p subgroup has size p squared. And so that type of subgroup is a little like, there's more groups that could have size p squared than just have size q. So let's look at the Ceelo q subgroups. So since n sub q is equal to p squared, we have p squared times q minus 1 elements in G of order q. Let me write that down and let everybody think about it for a second. Can you all see that? Okay. Is that it all legible? Trying to make this readable. So I think, Edith, this is kind of that peacock argument, right? This is the idea. You have your identity element here, and then you have your Ceelo subgroup of size q. So there are q minus 1 elements here together with e, and that makes up my, my Ceelo q subgroup there. And then the next one would be right here. You have the identity element together with another q minus 1 elements that have order q. See, these are all cyclic. Every one of them is cyclic of prime size, so their intersection is just e, right? And each of these non-identity elements has order q. So I've got q minus 1 of them in this feather. I've got q minus 1 of them in this feather, and we have p squared of those feathers, right? So there's p squared of these. Each one of them has q minus 1 elements of order q in them. So that's really what this sentence is explaining. The picture just kind of goes with the sentence. Does anybody need any clarification so far? So look at how many elements that is. So far, how many elements is that? That's p squared q, which is the whole group, minus p squared. So the question is, well, how much room is left in this group? Like, how much more space can we fill in with other elements? Well, we have some elements of the Ceelo p subgroups, right? Each Ceelo p subgroup has size p squared. So every Ceelo p subgroup has size p squared, and I want you to think about those elements. One of the elements there is, of course, e. But then every other element that is in a Ceelo p subgroup would have what kind of an order? Let's see, the order of an element has to always divide the order of whatever group it's in. So if I have a subgroup of size p squared, let me just draw it down here maybe. I have a subgroup of size p squared. It's got E in it, but all of the rest of these elements, can you guys see that down there? All of the rest of these elements that I'm drawing with these little dots, right? They all have order. They all have order p or p squared. Their order has to divide p squared. But in other words, none of those elements can be the same as any of the other elements that I already drew. All of these other feathers that are up here at the top have elements of order q in them. And now I'm drawing this additional subgroup where every element has order p or p squared. And so what that means is that we have, so each Ceelo p subgroup has size p squared, giving, what would it be? P squared minus 1 elements of order order p or p squared. And if you think about it, if you think about the total number of elements that we've already counted, we already had almost the whole group here. How many were we missing? Well, we were missing just p squared of the elements. Well, here you're going to get, in just one Ceelo p subgroup, you're going to get this many more elements. So you can't have q of those, right? You can't have q of these additional blobs down here. It is true that if I wanted to draw the other blobs for the Ceelo p subgroups, they might intersect. Like, they could intersect here, because the reason is, well, if you have two subgroups of size p squared, they could intersect in something bigger than just E, right? They could intersect in a subgroup of size p, because p does divide p squared. So that gets a little hairy, because you can have overlapping Ceelo p subgroups. But by the time you've taken care of all of the Ceelo q subgroups, you realize you only have room for one Ceelo p subgroup. Okay, so this gives G too many elements. Too many elements, and that is a contradiction. It's very similar to that one that we did in class about a week ago for groups of size 99. Actually, for groups of size 99, it fits exactly this kind of a format, right? 3 squared times 11. Yeah, so does that kind of help, Edith? Does it make sense?
Yes.
Are you good? Is anybody else having any issues with this? They want to ask. This is a really good problem to go over, just because it brings a lot of things into play. Okay, if not, I would love to hear, does anybody else have any questions on the homework that you guys are working on for today? Actually, I'll give you a chance to look at your paper while I erase. I'm going to go ahead and erase this. Remember, guys, that this is all being recorded. So if you're trying to scramble to copy everything down, try not to let it stress you out too much, because I'm going to have this up on the website within an hour or two after we're done with class. So you'll get a chance to pull this back up again if you need to. Okay. Anybody have any other questions from today's homework that you'd like me to talk about?
Yeah, I have one.
Robert, go ahead. Which one?
Number 1 from 9.5.
Okay, number 1 in 9.5. I'm going to open my book up to that page. Oh, this is very appropriate, because we have another group of size p squared times q. So 9.5, number 1, the size of the group is p squared q.
Your camera's a hair low.
I'm going to adjust that. Thank you. In fact, let me just back it up a little bit here. It might be good. Thanks for that. Okay, this time they actually tell us that p is smaller than q. And they actually also tell us that q is not congruent to 1 mod p. So these are all just the assumptions. And what we're going to try to do here is prove that G is abelian. Okay, we're going to prove that G is abelian. So I'm going to, again, start this off by using the third Ceelo theorem to sort of get a start on the analysis. So let me do that. In fact, maybe I'll do it over on this side. So let's look at the number of Ceelo P subgroups and the number of Ceelo Q subgroups and see what we can say. All right? Just like we always do. So the number of Ceelo P subgroups is one more than a multiple of P and has to divide Q. Okay? And the number of Ceelo Q subgroups is one more than a multiple of Q and has to divide P squared. This is what the third Ceelo theorem pretty much tells me immediately. Now, because P is smaller than Q, let's see what we can say here. If we look at the number of Ceelo P subgroups, it has to be a divisor of Q. So it either, n sub P either equals 1 or equals Q. Right? Those would be the two choices. The only numbers that divide Q would be 1 or Q. Okay. We'll come back and look at this in a second. For the n sub Q, what we can say is that n sub Q is either equal to 1 or P squared. Okay? I would like to argue that both of those numbers have to be 1. This is what I'm going to try to argue, that both of them is equal to 1. So let's see how we could do that. What would happen if n sub P was equal to Q? This is what I don't want, right? I'm trying to show that n sub P is equal to 1. Well, what if it was equal to Q? This would just mean that 1 plus pk is equal to Q. Does anybody see anything wrong with that?
Our hypothesis says that that can't be true.
Exactly right, Robert. Q is not congruent to 1 mod P. So this equation right here, 1 plus pk equals Q, is directly in violation of that. So this is a contradiction. This would imply that Q is congruent to 1 mod P. And so that is impossible. Okay? So therefore, n sub P is equal to 1. This is good. This is a good start on what we're trying to get here. N sub P is equal to 1. Now let's look at n sub Q. Right? There's 3 choices here for n sub Q. We would like n sub Q to be equal to 1. But let's think about the other 2 possibilities first. If n sub Q was equal to P, for example, would there be anything wrong with that? This would say that 1 plus QL was equal to P. So is there anything wrong with that?
Yeah, P is less than Q.
Yeah, up here,
otherwise.
Exactly. We said that P is less than Q. So if you look at this equation, how could 1 plus QL add up to P if P is already less than Q? So this actually implies that P is more than Q, and that's a contradiction as well. Okay, so we can certainly do that. We can certainly say that much. So that gets rid of that case. So what if n sub Q was equal to P squared? Because I don't like this possibility either. Let's see if we can get a contradiction out of this as well. I'm just kind of going through it step by step. Can you guys all see this? Is this good enough? So if n sub Q was equal to P squared, what does that tell me? It tells me that 1 plus QL is equal to P squared. So I'm going to just do a little bit of number theory here. Okay, so this should be hopefully pretty easy to think about. So this would imply that if I solve this thing, would everybody agree that this implies that Q divides P squared minus 1? Can you see that? Q divides P squared minus 1. And, sorry, the reason is that you can just subtract 1, and then you have Q times L equals P squared minus 1. But P squared minus 1 does factor, so let me factor it here. So this implies that Q divides P minus 1 times P plus 1. So P squared minus 1 can factor as a difference of squares. Okay? But Q is a prime, right? So if Q is a prime number, this means that one of two things is true. Q divides P minus 1, or Q divides P plus 1. Those are the possibilities. Okay? Ultimately, I'm looking for a contradiction here. Because we're saying, what if n sub q is equal to p squared? So I'm looking for a contradiction here. Can q divide p minus 1? Well, remember, p is less than q. So p minus 1 is definitely less than q. You cannot have a bigger number dividing a smaller number. So this is absolutely impossible because p is less than q. So I'm just going to squeeze that justification there. P is less than q, for sure. Okay, so now could q divide p plus 1, knowing that, let's see, p is the smaller of the two numbers? That actually means that p plus 1 is still less than or equal to q. If you look at this, right? Is everybody with me? So p plus 1 is still less than or equal to q. If I just come back up to my assumption, just to make this really clear up here. This just, p less than q means that p plus 1 is still less than or equal to q. So the only way that q could divide a number that's less than or equal to it is if this is actually an equal sign. Q equals p plus 1, right there. Okay, q would have to equal p plus 1. And guys, that is a contradiction again because q is not congruent to 1 mod p. All right, this would imply that, this implies that q is congruent to 1 mod p. And that is impossible. Okay, so modulo p, q would be equal to 1. So that's also impossible. Both of these possibilities turned out to be contradicted. And that means that n sub q cannot equal p squared either. Robert, are you with me?
Yep.
So I don't know what part of the question you wanted to ask me about. Maybe it's not this part, but at this point, I have hopefully convinced everybody within the sound of my voice that n sub p equals 1 and n sub q equals 1. We have normal subgroups of both of those prime power sizes. So I don't want to erase too quickly. Have people had a chance? Does anybody need me to wait to erase anything on the bottom half here? Okay, if not, I'm going to go ahead and erase this bottom part. This is the first main part of the argument, is based on the fact that there's only one Ceelo P subgroup and one Ceelo Q subgroup. We have normal Ceelo subgroups P sub P inside of G and P sub Q inside of G. Yeah, and what we can do now is exactly like the one I showed you guys last week. We can form the product subgroup. So P sub P times P sub Q, right? You remember this where you just do a multiplication here? This is actually a subgroup of G as long as these two subgroups are normal in G, we can form their product and we get a subgroup of G. This is by a homework problem. And I can ask myself, well, what's the size of that thing? Well, the thing is that P squared, so the P sub P has size P squared. So P squared would have to divide by Lagrange's theorem. So by Lagrange, there's a subgroup here. You see, let me just steal a little room here, right? Inside of this product group, we have the two Ceelo subgroups sitting as subgroups. So P sub P is inside of there, P sub Q is inside of there, and that means by Lagrange's theorem, I should have size bars here. By Lagrange's theorem, P squared divides that size, and so does Q.
Can you move the camera a little bit down, please?
You betcha. Is that better?
Yes, thank you.
You're welcome. So by Lagrange's theorem, we have inside of P sub P times P sub Q, we have this subgroup P sub P that has size P squared, and we have a subgroup P sub Q that has size Q. That means that both of those numbers divide the size of whatever this thing is that we're looking at. And that means that when you put that together, the whole P squared Q has to divide the size of this product. If P squared divides it and Q divides it, then so does P squared times Q, right? So we get that much. And that actually means that the P sub P times P sub Q is the whole G. So in other words, the size of P sub P times P sub Q is P squared Q, which means that, and I'll move in a second here, this means that this is the whole group G. Sorry. Okay, so we have the whole group G there. Now, the only thing left to show is that this is abelian. And you have this product here, P sub P times P sub Q, that's what G is. So you just have to grab, I think we did almost exactly the same thing in class. I'm gonna refer you back to, if you don't mind, Robert, I'm gonna refer you guys back to last week's notes where I think I was proving that every group of size 99 is abelian. It's exactly the same argument, except in that case, I was using specifically the numbers 3 and 11. Here, I'm just doing the same thing with the numbers P and Q. You just have to show that any two elements commute. Any two elements of G have the form of a product of something from this Ceelo subgroup times something from this Ceelo subgroup, and then you just go from there. Is that okay?
Yes.
Great. Does anybody have any questions either about this or another problem on the assignment? Everything good so far? I'm going to go ahead and erase this. Let's see, where did there it is. So I heard that it's raining in California. Is that right?
Certain parts.
I'm gonna, at the risk of messing up my Zoom session, I'm gonna bring you over here. This is just a quick little interlude. Can you see that? It is snowing like crazy outside.
Oh, wow.
It snowed like
Beautiful.
more than a foot already. And it's just been coming down all day. And so I'm staying inside. And
So
I think I might start up the fireplace tonight. Try to find a way to keep warm somehow. All right, so we're good on that. I tell you what, I'm gonna be around later in my virtual office hours to take some questions about the homework, if there's anything else that came up. Please submit them to the Dropbox folder. Do not just send me an email with the homework. Try to put them in the Dropbox folder. It'll save me a bit of effort for sure. So, okay, what I would like to do with the rest of the time we have today is practice some examples from the
Someone's asking for number 20 for section 9.3.
Oh, I didn't see that. Yes, I do see that now. Thank you. Number 20 from section 9.3. So suppose that this is for number 20. Let's suppose the size of our group, what's it say here? The size of the group is p to the k times m. And the assumption is that m is smaller than p. And it says prove that this group is not simple. Can somebody help with this one? This one I think is pretty fast if we just approach it the right way. Do I have anybody out there who maybe wants to give me a suggestion as what I should look at here?
Find the number of Ceelo P subgroups.
Okay, the number of Ceelo P subgroups. That sounds like a good idea. It's going to have the form 1 plus pk, and that has to divide the rest of the factorization of this number, which was m. But you see, we're actually already done here because m is less than p. So 1 plus pk, if it's going to divide m, it has to equal 1, right? So since m is less than p, n sub p is equal to 1, and that means that you get a normal Ceelo P subgroup inside of G. And that means G is not simple. Okie doke. So yeah, this third Ceelo theorem is really nice. It gets you a lot of mileage. Any questions on it? Okay. Let's do this. Let's take a break from working on the homework problems and just go through a few problems from these group works that we didn't get a chance to do together, because I really like these problems. And then, like I said, if you have more questions on the actual homework, you can certainly shoot me or you can stop by my Zoom session later tonight. I also forgot to mention, guys, I put up a new homework assignment. The next homework assignment is going to be due next Thursday. Now, because I'm not supposed to lecture on new material, I guess today and Tuesday, I'm going to be making a supplemental video. So you're going to want to watch that video because I was supposed to, normally I would have given a lecture today, but I couldn't. So I'm just doing group work and kind of having like office hours right now. But you'll want to watch that supplemental video, which I'll make, and then you'll be ready to do the homework for next Thursday. Okay. Let's do a few of these problems out of some of these group works, and then we can also do some of these next Tuesday if we don't finish them right now. So I'm going to look at group work number 6, problem 1A. It says, how many elements, I'll write it down for you in case you don't have it with you. How many elements of S7 commute with the cycle 1, 2. So this goes back a little bit, before the Ceelo theory, to something we talked about a little earlier. We're wanting to know specifically with the cycle 1, 2, how many elements commute with that cycle. This is really just asking us to find what? Can somebody tell me, what is this really asking me to find the size of?
The center?
Center is close, but the center is the elements of the group that commute with everybody. I'm just looking here at those elements that commute with the specific cycle 1, 2. So it's not the center, it's, what is it that we're looking for here?
Centralizer of that element.
That's right, it's the centralizer of that element. Thank you, Robert. Yeah, so what we're gonna try to calculate is the size of the centralizer of this cycle 1, 2. Okay, so this is the cycle 1, 2. And this is where I'm hoping you guys might recall our little, theorem from last week, that there's a nice relationship between the size of the centralizer and the size of the conjugacy class. So what we can do here is we can actually find the size of the centralizer by taking the size of G and dividing by the size of the conjugacy class. Now, what is the size of S7? Anybody?
7 factorial.
Exactly, 7 factorial. That's the size of S7. And the size of the conjugacy class of 1, 2, I have to remind you here, guys, that in the symmetric group, the conjugacy classes are just the cycle types, the different cycle types that we have. So we're really just asking, how many 2 cycles does S7 have? When I'm looking for this denominator, the size of the conjugacy class of 1, 2, it's just really asking, how many transpositions are there? Okay. Well, the answer to that is something that would be written in sort of a combinatorial way. It's really just something called 7 choose 2. I'm going to write it in that notation. You may or may not be that familiar with that. Let me write it a different way for you. You're really just trying to choose 2 elements to put into this cycle. So you could just say, well, there's 7 choices for the first number, and then there's 6 choices for the second number, except that the first number and the second number are completely interchangeable, and we shouldn't keep track of which one was first and which one was second. So I'm going to divide by 2 here. Okay, so that is the same thing as 7 choose 2, which you see on the bottom there. Okay, and so what does this come out to? Well, 7 factorial mostly cancels with 7 times 6. It leaves me with 5 factorial, and then I have a factor of 2 that flips up to the top. I believe that comes out to 240. Okay, so 7 factorial divided by 7 choose 2. There's 240 elements in S7 that commute with the cycle 1, 2. Any questions on that? Does this make some sense so far? Okay, I have a part B, which is just a slightly harder version of the same thing, but it's the same kind of problem. I'm going to just erase my question here and change what I'm actually looking for. So in problem 1B, we're going to ask how many elements of S7 commute with, I'm going to give you a different element here, which is going to be the element which has a cycle 1, 2, 3, followed by a cycle 4, 5, 6, 7. And so that's a 3 cycle multiplied by a 4 cycle. All of this is, of course, typed up in the group work, so you don't have to worry about writing every last little piece of this down. If you want to use your group work, you certainly can. So this is just a slight modification. it's the same idea. We're going to calculate the size of the centralizer of 1, 2, 3 multiplied by 4, 5, 6, 7, which means I'm going to put 1, 2, 3 times 4, 5, 6, 7 here. Okay, and now I need to fix the rest of this calculation now. So I'm going to go ahead, if you don't mind, I'm going to erase just this last part so that we can talk about what to fill in for the rest of this argument here. So the size of my group is still 7 factorial. But now I have to ask how many cycles, how many elements, I should say, of S7 have this cycle type, a 3 cycle multiplied by a 4 cycle. We have to think about that. So I'm going to break it down into 2 parts, the 4 cycle part and the 3 cycle part. The very first thing I need to decide as I'm building this 4 cycle and 3 cycle is which of the 7 numbers are participating in the 4 cycle. So I have a 4 cycle. Notice that all 7 numbers get used. 3 of them go into one camp, 4 of them go into the other. So I have to decide which of the numbers are going to be in the 3 camp and which of the numbers are going to be in the 4 camp. So I can do that as follows. I can say 7 choose 4 as the number of ways, and I'm using my fancy combinatorics notation for that. 7 choose 4, that's the number of ways of choosing 4 of my 7 numbers to participate in the 4 cycle. So a 4 cycle is just something like this, right? A, B, C, D. Now, once I've got my 4 numbers, A, B, C, D here, I have to ask, well, how many 4 cycles can I make out of those numbers? You know, I have A, B, C, D, but I also, you know, I have A, B, D, C, I have A, C, B, D, and so on. There's a bunch of them, right? The question is, how many ways can I make a 4 cycle out of those 4 numbers? Well, what you can do to count that is you can just say, I'm going to always put A first. When I make my cycle, whatever A is, I'm going to always put it first. And then I have, what is it, 3 factorial different ways to swap the B, C, and D around. Notice how I'm doing that here. The A is always first. And I can do that because the cycle goes around in a circle, right? It doesn't really matter where you start. So I'm just going to start with A. And then what matters is what comes after A, and then after that, and then after that. There are 3 factorial ways. I'm going to write that there. There are 3 factorial ways to arrange those numbers into that 4 cycle. That's just for the 4 cycle only.
You've lost me.
Okay, sure. That's okay.
So for the 4 cycle, you did 7 choose 4, which is the amount of ways that you can pull 4 out of 7.
If I have 7 people in a room and I'm going to choose 4 of them to play a game, I have 7 choose 4 ways to do that. So I'll write down what that actual number is in a minute. But just mathematically, we would write that as 7 choose 4. So we're choosing 4 people to play a game. After we've chosen those 4 people, we're now sort of putting them in order. We're saying, well, how do we want to make a cycle out of those 4 people?
I see. Okay.
So that's what the 3 factorial is doing. It's sort of, you know, making the arrangement of the 4 cycle. The first player, which is player A, we just put that person anywhere we want in the room. And then we put the B, C, and D around that first player in 3 factorial different ways. The B, C, and D are the things that we are rearranging.
I see.
This one's a little tricky. Don't get too bent out of shape about it. This isn't really even, to be honest with you, it's not really totally abstract algebra. This is more like combinatorics, actually. If you take Math 471, you're going to learn this like standard stuff for that. once I've got my 4 cycle arranged, I still have to arrange my 3 cycle. But the thing with the 3 cycle is that the three elements that were not chosen for the 4 cycle are automatically going to be in this 3 cycle. So I don't have to choose them anymore. They're already automatically going. Whichever 4 people went off to play the first game, the 3 players that are left are definitely in the second game. And so it's just a matter of how many ways can you arrange 3 letters ABC into a cycle.
Is that only 2 then?
And that's only 2. That's right. ABC and ACB. So all I'm going to do here is then multiply by 2. Okay, that's the whole expression. How can we now write that as an actual answer? Well, I'm going to show you here. We have 7 factorial on top. On the bottom, we have 7 choose 4. Let me just explain what that is. 7 choose 4 is actually, it's 7 factorial divided by 4 factorial times 3 factorial. This is a general formula for n choose k. Again, this really comes from combinatorics, so I won't bore you with this too much. But what you get for the formula for n choose k is n factorial divided by k factorial and n minus k factorial. Okay, so that's what you would have. And then you have this 3 factorial here and another factor of 2 like that. And I worked all of this out. And when you actually divide all of that out, you get actually just a final answer of 12. The 3 factorials actually cancel, and so do the 7 factorials. And so you just get 4 factorial divided by 2, which is 12. So there's only 12 elements in S7 that commute with that particular cycle. Okay? Some of the combinatorics is a little bit heavy on that. That's not really the focus here. The whole idea I want to make sure you know, of course, is that conjugacy classes are the same as cycle types. And so when I ask you how big is a certain centralizer, I want you to translate that into how big is the corresponding conjugacy class, which amounts to looking at cycle types. That's really the big idea from these examples, not so much the actual numbers that we're getting. So, okay, so that's one of the problems in the group work that I thought would be nice to review. Any questions? Okay, hearing no objections, I'm going to go on to another problem from that same group work. So let me look at number 2. And what it says is determine the isomorphism type of a Ceelo 3 subgroup of, we're going to do S3, S4, S5, S6, S7, and S8. That looks like a lot of work, but we're going to find out that it doesn't take too much work to answer this. Can everybody read it okay on the screen? Is it legible? Okay. Hearing no objections, I will.
It is to me.
Yes, it is.
Okay, good. Somebody chiming in that it's readable. That's great. It's a little hard for me to write on this board. I still need to try to figure out how to secure it a little bit better. So I think my handwriting is maybe 90% as good as it could be, but it's the best I can do for now. I'm doing my best. Okay, so guys, remember that on Tuesday, I stated the second Ceelo theorem to you, and the second Ceelo theorem told us that all Ceelo subgroups of a particular prime are isomorphic to each other. So what that means is that, you know, when I say what is the isomorphism type, I really do mean what is the isomorphism type. We can't have more than one answer here. Even if n sub 3 is bigger than 1, maybe there's more than one Ceelo 3 subgroup. That's possible, but what we know from the second Ceelo theorem is that there is only one isomorphism type. We might have several copies, several isomorphic copies of the same subgroup that have that correct size. But from an isomorphism standpoint, they're all the same. They all look like the same group. Okay, so this question is asking us to figure that out. Let's start with S3. Okay, so S3, first of all, what is the size of S3? Of course, it's 3 factorial, which is 6. And I'm even going to go ahead and factor that. It's 2 times 3. So in this problem, guys, in this problem, we don't care how many, we're not asking how many Ceelo 3 subgroups are there. I know on a lot of the homework problems, that was what we were doing. We were counting how many Ceelo subgroups we have. That's not what we care about here. All I want to know is what is my Ceelo 3 subgroup isomorphic to? Well, let's just take a look here. What is the size? What is the size of my Ceelo 3 subgroup in this case? What is its size?
3.
Just 3, right? Okay, so if it's a group of size 3, do we know what group it is? What is it?
Z3.
Exactly, it's a cyclic group of size 3. So in this case, my Ceelo 3 subgroup is isomorphic to Z3. Pretty straightforward. It's only got size 3, so it's got to be that. Okay, let's go on to S4. Now, when I look at S4, the size of S4 is 24. I'm going to go ahead and factor that right away. That's just 2 cubed times 3. So in this case, how big is my Ceelo 3 subgroup?
3 as well.
It's still 3, right? It's still 3. So my P3 is still isomorphic to Z3. Same answer, right? We get the same result for a Ceelo 3 subgroup of S4. How about S5? So for S5, let's see, the size of S5 is 5 factorial, which is 120. That, how does that factor out? That is 2, let's see, 120.
Same as before times 5.
Say it again?
It's the same thing as S4, but times 5.
Right. Oh, exactly. So it's just 2 cubed times 3 times 5. Thank you. Of course. I'm a little slow over here in this Rocky Mountain air. Okay. What's the size of the Ceelo 3 subgroup in this case? The largest power of 3 that divides into the size of the group is still
The same,
3
right?
to the first power, right? So I still get Z3. So far, this is kind of a boring problem. Let's go to S6, though. When I go to S6 and I look at the size of S6, I'm going to throw in another factor of 2, so it's going to become 2 to the 4th, and another factor of 3, which means it's going to be 3 squared. Can you guys still see that? Is it coming through on the bottom there? Okay. So what is the size of my Ceelo 3 subgroup this time?
9.
This time it has size 9. Exactly. What do you guys know about groups of size 9? So this time, let me come over here. The size of my Ceelo 3 subgroup is 9. So do we know what the isomorphism type of that is?
Don't we know it's abelian?
Robert, good comment, because it's a group of size prime squared. Any group of size prime squared is always abelian. What are the abelian groups of size 9 that you know of?
Z3 cross Z3 and Z9.
Okay, Z3 cross Z3 or Z9. So this time we have two choices. And I'm wondering if anybody can help me out with that. Is this isomorphism type going to be Z3 cross Z3, or is it going to be Z9? We have to think about, I mean, both of those groups are abelian, of course. We have to ask ourselves, what's the difference? What's the main difference between Z3 cross
order?
Z3 versus Z9?
One is cyclic.
Okay, so Z9 is cyclic, right? Actually, Z9 has elements of order 9,
That's right.
right? I mean, you have a generator. You have a generator for that cyclic group. That generator will have order 9. That generator for the cyclic group Z9 would have order 9. Does S6 have any elements of order 9 in it?
No.
I don't think so. Let me show you why. Like, what are the elements of S6? We have E, right? We have cycles AB. We have cycles ABC, right? We can go like that for a while, all the way up to A, B, C, D, E, F. These are the sort of the cycle types in S6. And my point is that if you think about the orders of these cycles, you're not going to get 9 out of this.
The
mean,
max would be 6.
I'm sorry?
Would the max order be 6? Maximum order you could have?
I think you're right. In this case, the maximum order that you could get would be 6. I mean, you can do things like, you can take a 4 cycle times a 2 cycle, and you can do various combinations, but the least common multiple of these cycle lengths will definitely never be 9. You do not have any elements in S6 of order 9. So surely this subgroup doesn't have any elements of order 9 either. This Ceelo 3 subgroup that we're talking about over here, guys, I hope I'm convincing you that it is isomorphic here to Z3 cross Z3. That's the only other choice, right? That's the only other choice. I'm just doing it basically by process of elimination. I'm saying, well, this group has no elements of order 9 in it, so you can't have Z9 as a subgroup. Or you don't have an isomorphism type of Z9 in there. Now, it turns out that when you go on to S7 and S8, nothing changes. Nothing changes. You still have, for S7 and S8, you still have a Ceelo 3 subgroup that is going to have size 9, and there will still be no elements of order 9. So I won't write it down now. It's certainly in the solutions to the group work that you can look up later. But the isomorphism type of the Ceelo 3 subgroups in S6, S7, and S8, they are all isomorphic to Z3 cross Z3, as opposed to Z9. Okay? Everybody good with that so far? Okay, let's see if we have time to do one more of these. These are all off of group work number 6. Let's do number 3 real fast. I think I have time to do that. I was hoping to get to the next group work as well, but I don't think I'm going to. So just to give you a quick little heads up, I'm going to, next Tuesday, we're also going to have like a non-lecture class. So I'll probably do that other group work with you on Tuesday next week. That's group work number 7. And I'll also answer questions on the homework that's due next Thursday. So if you come in next Tuesday for the office hour that I'm going to be here for, you can ask questions on that. I probably won't take questions on it next Thursday during our regular class time, but Tuesday I would. So that's some incentive to start early. To be able to start all of the homework for next week early, you're going to need to watch the video that I'm going to post. So I'll make another video. I'll post it. I'll probably even email you to let you know where it is and that I've done it. But that's kind of what I'm thinking of doing. Okay. So let's see if with the, what do we have, like 7 minutes left today? Let's see if I can just do the next problem off of this current group work number 6. Let me do problem number 3. And this says, show there is no simple group of size 380. Okay. No group of size, no simple group of size 380. So the very first thing that we would want to do, of course, is factor that number, right? So let me write down the factorization right here next to the question. 380 turns out is the same as 2 squared times 5 times 19. So I'll just give you that factorization. That's not really the main point. So in terms of how to proceed, we're trying to come up with a normal subgroup. And that third Ceelo theorem has been a great tool for this, right? We've been able to use the third Ceelo theorem using the size of the group to take the primes that are involved and count how many Ceelo P subgroups we have. Now, as we've done many times in the past, I'm going to start with the largest prime first because I usually think that that's a big help. So let me look at the number of Ceelo 19 subgroups that we have. 19 is the biggest prime that is here. So this is going to be the form 1 plus 19k, and it has to divide the rest of this factorization. The rest of this factorization, 2 squared times 5, well, that's 20. And so, ooh, that actually gives me a couple of possibilities here, doesn't it? That gives me a couple of choices. N sub 19 could equal 1, or it could equal 20, because 1 plus 19k could equal 20. So I can't rule out 20 quite yet. So because I'm not able to just immediately rule out the possibility of 20 Ceelo 19 subgroups, I'm going to look at my next largest prime, which is 5. So let's look at that. N sub 5 is going to have the form 1 plus 5L. And it has to divide the rest of the factorization of this number. So the rest of the factorization is actually 19 times 4. 19 times 4 is 76, I believe. Okay, so we get 1 plus 5L divides 76. So now we have to actually think about this one as well. What are the numbers that would divide 76? Obviously 1. And then we have to think about what other numbers this could be, right?
You can look at the prime factorization of 76.
Absolutely. So the factorization of 76 is 2 squared times 19, right? So the question is, what are the possibilities? So 1 plus 5L, if it's going to divide 76, it either has to equal 1 or 2 or 4 or 19 or 38, right? Or 76. These are all of the divisors of 76. Actually, a number of the form 1 plus 5L has to end in a 1 or a 6, if you think about it. 1 plus 5L has to end in a 1 or a 6. So it can't be any of these choices in the middle. But it could be 76. That is actually possible. Okay, so 1 plus 5L has to divide 76, and in fact, it might even be equal to 76. So all you have to do now, guys, is the standard counting argument. Let's assume n sub 19 equals 1 and n sub 5 equals 1. I'm sorry. Let's assume that I said that wrong. N sub 19 equals 20, and assume that n sub 5 is equal to 76. All we have to do, guys, and we only have 2 minutes to do it, so it's a good thing it's not very hard. We just have to count the elements now. And we're going to get more than 380 elements, right? So this gives, what does this give me? This gives me 76 times 4 elements of order 5. I just want to make sure everybody understands that. We have 76 Ceelo 5 subgroups, and each one of those Ceelo 5 subgroups has 5 elements in it. One of them is E, but then there's 4 other non-identity elements in each one of those Ceelo 5 subgroups. So there's 4 elements of order 5 in each of the 76 Ceelo 5 subgroups, right? And then similarly, we get 20 times 18 elements of order 19. So using the other piece of information, we get 20, there's 20 different Ceelo 19 subgroups. Each of them has 18 non-identity elements, which would each have order 19. Now you just have to add all of this up. 76 times 4. 76 times 4 plus 20 times 18. And I guarantee you that that is bigger than 380, right? It's too many elements. So this is a contradiction. That's a contradiction. And so at least one of these two assumptions has to be wrong, right? So either n sub 19 equals 1 or n sub 5 equals 1. And that means you've got a normal subgroup inside of G. It's not a simple group. Okay, so this already implies G is not simple. I guess I never used the letter G for the group, but that's of course what I'm talking about. Okay, I'm hoping this is making some sense. I can't see very many of your faces today. I saw a lot more of you. I could actually see you on Tuesday, a lot of you. Today, a lot of you have no video, so I'm trusting you to let me know if there's any question. So okay, I see some people chatting on the group chat on the side here. I'm hoping that everything's making some sense there. I'm going to go ahead and wrap this up for now. And if there are any questions, more questions about this or anything else, why don't you guys let me know? I'm going to go over to my office hour room. This feels so strange. I feel like I'm supposed to walk somewhere, but I don't have to walk anywhere. I just have to like close this session and open another one. If you missed anything from today or you just want to watch it again, I'm going to compile this video and post it under the class lectures. And again, next Tuesday, I will also not be doing any new material. I will just take homework questions and do some more group work with you. But I am, in the meantime, going to make a video It's snowing outside. What am I supposed to do for the next 5 days? I've got to do some math. So I probably will do that, and I'll keep you guys posted, okay? Thanks
You
for
can
coming
build
in
a
today.
snowman.
Pardon me?
You can build a snowman.
I can make a snowman. Maybe I'll do that. If I do that, I'll take a nice picture of it and find some way to connect it to math. All right. Thanks, guys. I appreciate it. I will see you again soon. Thanks for coming, and stay safe out there.
Bye.
Bye-bye.